The universe holds terrors beyond human comprehension, places so profoundly disturbing that they challenge everything we thought we knew about existence itself. We often imagine the most frightening cosmic phenomena as violent and energetic: black holes tearing matter apart, supernovae exploding with unimaginable force, gamma-ray bursts that could sterilize entire galaxies. But the truly unsettling places in the cosmos aren't defined by their violence. They're defined by their absence. The most terrifying regions in the observable universe are the voids, incomprehensibly vast expanses where almost nothing exists, stretching across hundreds of millions of light-years of empty darkness that makes the space between stars look crowded by comparison. When we look up at the night sky, we see what appears to be a universe filled with stars, galaxies, and cosmic wonders. This perception, however, is fundamentally misleading. We live in one of the universe's rare neighborhoods where matter actually congregates. The reality is that the overwhelming majority of space contains virtually nothing at all. Cosmic voids are not simply regions with fewer galaxies than average. They are massive volumes of space that have been almost completely abandoned by matter itself. These regions contain so few galaxies that if you were transported to the center of one, you might see nothing but darkness in every direction for hundreds of millions of light years. No distant galaxies to orient yourself, no stellar landmarks, no cosmic signposts, just an endless, consuming emptiness that would make the vast distances between stars in our galaxy seem intimate by comparison. Understanding what these voids actually are requires us to fundamentally reconsider what we mean by empty space. In everyday language, we might call a room empty if it contains no furniture, even though it's filled with air, light, and countless particles. In astronomy, empty space between stars still contains gas, dust, cosmic rays, and the ever-present cosmic microwave background, radiation. But cosmic voids represent emptiness on an entirely different scale. These are regions where the very fabric of space contains almost no galaxies whatsoever. The fundamental building blocks of cosmic structure are simply absent, where we would statistically expect to find thousands of galaxies clustered together through gravitational attraction. We instead find fewer than 100 scattered across volumes larger than millions of light years in every direction. The most unsettling aspect of these voids is not just their size or emptiness, but what they reveal about the nature of existence itself. We like to think of the universe as fundamentally full of matter and energy, with empty space being the exception. The voids force us to confront the opposite reality. The universe is fundamentally empty, and matter is the rare exception. We exist on a tiny island of substance floating in an ocean of nothingness, so vast that our entire observable universe might be just one small archipelago in an infinite sea of void. This realization transforms our cosmic perspective from one of abundance to one of profound scarcity, suggesting that existence itself is a statistical anomaly in a cosmos that overwhelmingly prefers to be empty. The story of humanity's discovery of these terrifying empty regions begins on a seemingly ordinary day in 1981, when astronomer Robert Kirshner and his colleagues were conducting what they thought would be a routine galaxy survey. They were mapping the distribution of galaxies in a region of space in the direction of the constellation. Boötes using redshift measurements to determine distances and create a three-dimensional picture of cosmic structure. What they expected to find was a relatively uniform distribution of galaxies, perhaps with some clustering here and there as gravity pulled matter into groups. What they actually discovered would fundamentally change our understanding of the universe's large-scale structure and introduce the astronomical community to one of the cosmos's most disturbing features. As the data accumulated and the team plotted the positions of galaxies, a pattern emerged that made no sense. According to existing theories, there should have been thousands of galaxies in the surveyed region. The volume of space was certainly large enough to contain them, and there was no obvious reason why this particular patch of the universe should be any different from others. Instead, they found fewer than 100 galaxies scattered across a region spanning 330 million light-years. The initial reaction was that something must be wrong with their instruments or their methodology. Perhaps there was some systematic error in their observations, or maybe they had made a calculation mistake somewhere in their analysis. They checked and rechecked their work, but the conclusion remained inescapable. They had discovered a hole in the universe, a vast region of space that contained almost no galaxies whatsoever. The announcement of the Boötes Void sent shockwaves through the astronomical community. This wasn't supposed to be possible according to the prevailing understanding of how the universe should be structured. Theories of cosmic evolution suggested that matter should be distributed relatively uniformly on the largest scales, with galaxies forming wherever sufficient density fluctuations existed in the early universe. The existence of a void. This enormous, which became known as the Boötes Void or the Great Void, challenged these assumptions and forced cosmologists to reconsider the fundamental processes that shape the universe's large-scale structure. Some initially speculated that the void might be evidence of exotic physics, perhaps related to phase transitions in the early universe, or even to the explosive expansion of bubbles in the cosmic fabric. Others wondered if this might be an observational artifact, some trick of light or perspective that made a normal region appear empty when viewed from our particular vantage point. As additional observations confirmed the reality of the Boötes Void and other similar structures began to be discovered throughout the universe, astronomers had to accept that these enormous empty regions were genuine features of cosmic architecture, rather than anomalies or errors. The void wasn't completely empty. Those scattered dozen or so galaxies did exist within its boundaries, but it was far emptier than any region of similar size had any right to be. The density of galaxies within the void was roughly 10% of what would be expected in an average region of space, meaning that 90% of the matter that should have been there was simply absent, having been drawn away to the void's boundaries where it formed walls and filaments of enhanced density. The true terror of the Boötes Void becomes apparent only when you try to genuinely comprehend its scale, which is almost impossible for human minds that evolved to understand distances measured in meters and kilometers. 330 million light-years is not just a large distance. It's a distance so vast that it breaks our intuitive understanding of space itself. To travel 1 light-year at the speed of a commercial airliner would take about 1 million years. To cross the Boötes Void at this speed would require 330 trillion years, or roughly 24,000 times the current age, of the entire universe. Even traveling at the speed of light, the absolute cosmic speed limit, it would take 330 million years to cross from one side of the void to the other. But perhaps the most effective way to understand the scale involves a thought experiment that astronomers themselves have proposed. Imagine if our Milky Way galaxy, instead of being located in its actual position within the Virgo supercluster, were somehow transported to the center of the Boötes Void. From this new vantage point, human civilization would have evolved under a fundamentally different night sky. Our nearest neighboring galaxy would not be Andromeda, visible as a fuzzy patch just 2.5 million light-years away. Instead, the nearest substantial galaxy would be more than 100 million light-years distant, so far away that it would be completely invisible to the naked eye. our astronomers would not have discovered other galaxies in ancient times when philosophers first turned telescopes toward the heavens. We would not have discovered them in the 19th century when larger instruments first resolved nebula into collections of stars. We would not have discovered them in the early 20th century when Edwin Hubble determined the distance to Andromeda and proved that our galaxy was not alone in the cosmos. Instead, if we lived at the center of the Boötes Void, we would not have definitively detected other galaxies until the 1960s, when instruments finally became sensitive enough to detect the incredibly faint and distant galaxies at the void's boundaries. For the entire history of human civilization, up until that point, we would have believed, quite reasonably based on all available evidence, that our galaxy was the entire universe. We would have thought we were alone in a cosmos that consisted solely of the Milky Way, surrounded by infinite emptiness. The entire development of cosmology, our understanding of the universe's origin and fate, our theories about the nature of space and time, all would have been fundamentally different. We would have developed our physics and astronomy in a state of profound cosmic isolation, looking out into a darkness so complete that it would have seemed to confirm that nothing else existed beyond our galactic shores. This thought experiment reveals the truly disturbing implication of voids. They suggest that our perception of the universe as full of galaxies and rich with structure is an accident of our location. We happen to evolve on a planet, in a galaxy, in a region of space where matter congregates. Had we instead originated in one of the many void regions, our entire understanding of reality would be fundamentally limited by the accident of our position. It raises the unsettling question of how many other aspects of the universe we might be missing because of where we happen to live, and whether there might be entire categories of cosmic phenomena or structures that are invisible to us simply because we're not positioned to observe them. The terror deepens when we consider the possibility that we don't just live near a void. We might actually be inside one right now. This disturbing hypothesis emerged from careful studies of the local distribution of galaxies and the cosmic microwave background radiation. In the 2000s, astronomers Ryan Keenan, Amy Barger, and Lennox Cowie proposed that our local group of galaxies, including the Milky Way, exists within an underdense region of space that extends roughly 2 billion light-years in diameter. This structure, which they called the KBC Void after their initials, would be one of the largest voids ever discovered, and we would be living inside it. The evidence for the KBC Void comes from multiple sources. Observations show that the density of galaxies in our local cosmic neighborhood is lower than the universal average. When astronomers map the distribution of matter around us, they find that we appear to be in a region where galaxies are more spread out than they should be, according to standard cosmological models. Additionally, our measurements of the Hubble constant, the rate at which the universe is expanding, seem to vary depending on how we measure it. Some methods that look at the local universe give different results than methods that examine the cosmic microwave background from the early universe. One possible explanation for this discrepancy is that we live in an underdense region where space expands slightly faster than the cosmic average, causing our local measurements to differ from the global values. If the KBC Void hypothesis is correct, it has profound implications for our understanding of cosmology. Many of our most fundamental measurements about the universe, how fast it's expanding, how much dark matter and dark energy it contains, how old it is, are based on observations we make from our particular location in space. If that location happens to be in a void where conditions are not representative of the universe as a whole, then our measurements might be systematically skewed. We might be drawing conclusions about the entire cosmos based on observations from an atypical region, similar to how an ecologist who only studied desert environments might draw incorrect conclusions about Earth's overall climate and biodiversity. The possibility that we live in a void creates an almost existential uncertainty about our cosmological knowledge. We've spent centuries developing increasingly sophisticated theories about the universe's origin, evolution, and ultimate fate. We've measured cosmic parameters with ever-increasing precision, confident that our observations from Earth and near-Earth space can tell us about the universe as a whole. But if we're inside a void, we're essentially observing the cosmos from inside a cosmic bubble where conditions are unusual. It's like trying to understand the ocean while living inside an underwater air pocket. Your immediate observations would be accurate for your local environment, but they might not reflect the true nature of the surrounding reality. This uncertainty is particularly unsettling because there's no easy way to verify whether we're actually in a void or not. We can't simply travel to another part of the universe to check if things look different from there. We're stuck with our particular vantage point, left to wonder whether what we see is representative or exceptional. To understand how these cosmic voids come into existence, we need to examine the early universe and the fundamental forces that shape cosmic structure over billions of years. The current scientific understanding is that voids are not primordial features that existed since the Big Bang, but rather natural consequences of how gravity sculpts the distribution of matter over cosmic timescales. In the earliest moments after the Big Bang, the universe was remarkably uniform, with matter and energy distributed almost evenly throughout space. Almost uniform, but not perfectly so. There were tiny density fluctuations, regions where matter was slightly more concentrated, and regions where it was slightly less dense. These fluctuations, which we can observe as temperature variations in the cosmic microwave background radiation, contained the seeds of all future cosmic structure. As the universe expanded and cooled, gravity began to amplify these initial density differences. Regions that were slightly denser than average had slightly stronger gravitational fields, which attracted surrounding matter and made them even denser. This created a positive feedback loop. Denser regions attracted more matter, became denser still, and attracted even more matter. Meanwhile, regions that started out slightly less dense than average lost matter to their denser neighbors, becoming progressively emptier over time. This process, which cosmologists call gravitational instability, caused the initially uniform distribution of matter to become increasingly clumpy over billions of years. But gravity doesn't just pull matter together randomly. It does so in specific patterns determined by the geometry of space and the initial distribution of density fluctuations. Instead of matter collapsing into uniform spheres, it collapses into a structure that cosmologists call the cosmic web, a vast network of filaments, walls, and nodes where matter congregates, separated by enormous voids where matter is sparse. Think of it like soap bubbles clustering together. The soap film forms walls and edges where bubbles meet, while the interior of each bubble contains nothing but air. In the cosmic web, galaxies and galaxy clusters form along filaments and walls like beads on strings, while the voids occupy the spaces between these structures, growing larger as more matter is drawn out of them toward the denser regions. The process of void formation and growth is ongoing. Even today, matter continues to flow out of underdense regions toward overdense ones, causing voids to expand while filaments and clusters become more concentrated. This is not happening because the voids are actively pushing matter away. There's no repulsive force emanating from their centers. Rather, it's simply that the gravitational attraction of the matter-rich regions is continuously pulling material away from the matter-poor ones. A particle located in a void experiences gravitational attraction toward all the surrounding massive structures at the void's boundaries, and the net effect of all these attractions is to pull the particle toward the nearest filament or wall. Over billions of years, this process has emptied out vast regions of space, creating the voids we observe today. What makes voids particularly fascinating is that they grow over time. Unlike galaxies or galaxy clusters, which reach a certain size and then maintain relatively stable structures, voids continuously expand as the universe ages. The boundaries of a void are not fixed walls, but rather transitional zones, where the density gradually increases from the nearly empty interior to the denser surrounding regions. As cosmic time progresses, matter at the edges of voids gets pulled away toward nearby filaments, causing the boundary to move outward and the void to encompass a larger volume. This means that the voids we observe today are larger than they were in the past and will be even larger in the future. In a sense, voids are like cosmic sinkholes slowly growing as matter drains away from them. Except there's no bottom to the sinkhole, just an ever-expanding sphere of emptiness. Among the catalogue of known voids, one stands out for its almost unbelievable emptiness. The Giant Void, located approximately 1.5 billion light-years away in the direction of the constellation Canes Venatici, represents an extreme example of cosmic emptiness that challenges our understanding of structure formation. This void encompasses a volume so vast that statisticians had initially calculated its existence should be highly improbable according to standard models of cosmic structure formation. The numbers associated with the Giant Void are staggering. Across a region where we would expect to find roughly 2,000 galaxies based on the average density of the universe, astronomers have identified only 17. 17 galaxies in a space that should contain 2,000. That's less than 1% of the expected number, representing a deficit so extreme that it pushes the boundaries of what our theories can comfortably explain. When the Giant Void was first characterized in detail, some astronomers questioned whether such severe underdensity was even possible within the framework of standard cosmological models. The formation of voids relies on matter draining away from underdense regions, but the process has limits based on how much time has passed since the Big Bang and how efficiently gravity can redistribute matter. For a void to be this empty, either it must have started with an unusually low density in the early universe, or there must have been extraordinary efficiency in evacuating matter from the region over cosmic time. The 17 galaxies that do exist within the Giant Void are themselves objects of intense interest. What makes a galaxy able to survive in such an underdense environment? Most galaxies form and evolve within the context of groups and clusters, where interactions with neighboring galaxies drive their development. These interactions can trigger bursts of star formation when galaxies collide or merge. They can strip gas from galaxies through gravitational and hydrodynamic effects, and they provide the dense environment necessary for certain types of galactic evolution. But the galaxies in the Giant Void have none of these advantages. They are profoundly isolated, separated from their nearest neighbors by tens of millions of light-years of nearly empty space. Their evolution has been shaped primarily by internal processes rather than external interactions, making them cosmic hermits whose development followed a very different path from galaxies in more typical environments. Statistical analysis of the Giant Void reveals just how anomalous it is. Cosmologists use sophisticated computer simulations to model how structure should form in the universe, given our understanding of gravity, dark matter, and dark energy. These simulations create virtual universes and evolve them forward in time, allowing researchers to examine what kinds of structures emerge and how common different features should be When these simulations are run thousands of times with slightly different initial conditions, they produce a wide range of structures, including numerous voids of various sizes. But voids as large and empty as the giant void appear in these simulations very rarely. Depending on the specific model and assumptions used, the probability of finding a void this extreme, in a volume the size of the observable universe, ranges from quite unlikely to extraordinarily improbable. This statistical tension doesn't necessarily mean our theories are wrong. Unlikely events do occur, and observing one improbable structure in a universe containing billions of voids isn't necessarily cause for alarm, but it does suggest that the giant void is near the edge of what standard cosmology predicts should exist. If we were to discover several more voids with similarly extreme properties, it would force us to reconsider our models of structure formation, or possibly even our understanding of the fundamental forces shaping the cosmos. The giant void thus serves as a test case for our theories, a natural experiment that probes the limits of cosmic structure formation. The giant void also raises intriguing questions about the maximum possible size and emptiness of cosmic voids. Is there a theoretical limit to how large a void can grow? Can voids become even emptier than the giant void, approaching absolute nothingness with zero galaxies across comparable volumes? The answers to these questions depend on the subtle details of how structure forms in the early universe and how efficiently gravity can evacuate matter from underdense regions. Current theories suggest that there should be a maximum size for voids based on the horizon distance in the early universe, the distance beyond which regions couldn't have influenced each other due to the finite speed of light. Voids shouldn't be larger than this distance, because their formation requires initial underdensities that are coherent across space, and such coherence can only exist up to the horizon scale. But the giant void approaches this theoretical maximum, suggesting that either our models of the horizon scale need refinement, or that we're observing one of the most extreme possible examples of this type of structure. The relationship between cosmic voids and the cosmic microwave background radiation provides one of the most intriguing connections between the largest structures in the universe and our observations of its earliest light. The cosmic microwave background, or CMB, is the afterglow of the Big Bang, radiation that has been traveling through space for over 13 billion years since it was released when the universe first became transparent to light. This radiation fills the entire sky and is remarkably uniform in temperature, varying by only about 1 part in 100,000 from place to place. But within that incredible uniformity are tiny temperature fluctuations that tell us about the distribution of matter and energy in the early universe. What scientists discovered is that these fluctuations are not only signatures of the past, they're also affected by structures the light passes through on its journey to us, including cosmic voids. The connection between voids and the CMB involves a subtle effect called the integrated Sachs-Wolf effect, named after the physicists who first predicted it. Here's how it works. Photons traveling through space are affected by the gravitational fields they encounter along the way. When a photon falls into a gravitational potential well, such as falling toward a massive cluster of galaxies, it gains energy and becomes slightly bluer. When it climbs back out of that potential well, on the other side, it loses energy and becomes redder. In a static universe, these two effects would cancel out perfectly, with the photon exiting the gravitational well at exactly the same energy it had before entering. But our universe is not static, it's expanding, and that expansion is accelerating due to dark energy. This acceleration means that gravitational potential wells are becoming shallower over time as space expands. When a photon falls into a potential well, then spends some time crossing it while the universe expands, the well is slightly shallower by the time the photon exits than it was when the photon entered. This means the photon keeps a tiny bit of the energy it gained falling in. It doesn't lose quite as much energy climbing out because there's less depth to climb. The net result is that photons passing through overdense regions, like galaxy clusters, gain a small amount of energy and appear slightly hotter than average. Conversely, photons passing through underdense regions like voids experience the opposite effect. They start by climbing out of the void, moving from higher to lower density. Then the universe expands while they cross it, and by the time they're falling back into the denser regions at the far side, those regions have grown more dense. The net effect is that photons crossing voids lose energy and appear colder. This means that particularly large supervoids should create cold spots in the cosmic microwave background. Regions where the CMB appears slightly cooler than average, not because of conditions in the early universe, but because of the structures the light passed through during its journey to us. The effect is small, typically just a few microkelvin, but it's detectable with sensitive instruments. Several potential supervoid cold spot correspondences have been identified, but the most famous and controversial involves the largest anomaly in the CMB, the cold spot in the constellation Eridanus. The CMB cold spot is a region of the microwave background that appears significantly cooler than typical fluctuations would predict, with temperatures about 70 microkelvin below average across a region about 10 degrees in diameter. On the sky, when this anomaly was first identified in data from the Wilkinson Microwave Anisotropy Probe, it was puzzling because it seemed too large and too cold to be easily explained by standard models of fluctuations in the early universe. One proposed explanation was that this cold spot might be caused by the integrated Sachs-Wolf effect from an enormous supervoid lying between us and the surface of last scattering where the CMB originates. Subsequent observations appeared to support this hypothesis when surveys identified what became known as the Eridanus supervoid, a vast underdense region approximately 1 billion light-years across, located in the direction of the cold spot. This structure seemed to be perfectly positioned to explain the CMB anomaly. Photons from the Big Bang passing through this enormous void would lose energy, creating the observed cold spot. The correspondence was compelling, and many researchers accepted that the mystery had been solved. However, the story became more complicated with additional observations and more detailed analyses. Some studies questioned whether the Eridanus supervoid was actually large enough and empty enough to produce the full magnitude of the cold spot through the integrated Sachs-Wolf effect. The calculations suggested that while the supervoid would certainly create some cooling, it might only account for about 30% of the observed temperature deficit. This raised the possibility that the cold spot might be caused by a combination of factors, partly the supervoid effect, partly an unusual fluctuation from the early universe, and possibly other effects we don't yet fully understand. The debate over the Eridanus supervoid and the cold spot highlights the challenges of connecting structures we observe in the modern universe with features in the cosmic microwave background. The light from the CMB has traveled over 13 billion light-years to reach us, passing through countless structures along the way. Disentangling all these effects and determining how much each one contributes to what we observe is enormously complex. It requires detailed models of how structure has evolved along the line of sight, precise measurements of the sizes and densities of intervening voids and clusters, and sophisticated statistical analysis to separate signals from noise. Regardless of whether the Eridanus supervoid fully explains the cold spot, the general principle remains valid. Large voids do affect the cosmic microwave background through the integrated Sachs-Wolf effect. and this provides us with a powerful tool for studying both the voids themselves and the expansion history of the universe. By carefully mapping correspondences between known voids and temperature fluctuations in the CMB, astronomers can test our models of dark energy and cosmic acceleration. The magnitude of the integrated Sachs-Wolf effect depends on how fast the expansion of the universe is accelerating, which in turn depends on the properties of dark energy. More acceleration means stronger effects, while less acceleration means weaker effects. By measuring the actual temperature shifts associated with known voids and comparing them to theoretical predictions, we can constrain the equation of state of dark energy and potentially distinguish between different models of what's causing cosmic acceleration. The question of what it would be like for an intelligent civilization to evolve inside a cosmic void provokes both scientific and philosophical contemplation. Imagine a species arising on a planet orbiting a star in one of those 17 lonely galaxies scattered through the giant void. From their perspective, the universe would appear profoundly different from what we observe from our vantage point in a relatively galaxy-rich region. Their night sky would be nearly empty, a vast dome of darkness punctuated by the stars of their own galaxy, but containing perhaps only 2 or 3 other galaxies visible even to their most powerful telescopes. Where we can observe thousands of galaxies with modest instruments and millions with sophisticated surveys, they would struggle to find even a handful. How would this cosmic isolation affect the development of their astronomy and cosmology? In our own history, the observation of galaxies beyond the Milky Way was crucial to understanding the scale and nature of the universe. When Edwin Hubble measured the distance to Andromeda in the 1920s and proved it was far outside our galaxy, it revolutionized our cosmic perspective. When he subsequently discovered that galaxies were receding from us with velocities proportional to their distance, it provided the first evidence that the universe was expanding. These observations formed the foundation of Big Bang cosmology and our modern understanding of cosmic evolution. But a civilization in a void might never make these discoveries, or might make them only after centuries of additional technological development. Without nearby galaxies to observe, they would have no clear evidence that their galaxy was not the entirety of the universe. They might develop theories about cosmic origins and evolution, but these theories would lack the empirical foundation that comes from observing the diverse population of galaxies at various distances and evolutionary stages. They might discover the cosmic microwave background radiation and correctly interpret it as evidence of a hot early universe, but without observations of galactic redshifts and the Hubble expansion. Connecting this ancient radiation to a coherent picture of cosmic evolution would be far more difficult. Perhaps most significantly, a void civilization would have a fundamentally different understanding of humanity's place in the cosmos, or rather, their own species' place. We've learned through astronomy that we occupy no special position in the universe. Our planet is one of several in an ordinary solar system, orbiting an average star in an unremarkable galaxy, located in a typical region of the cosmic web. This principle, sometimes called the Copernican principle or the principle of mediocrity, has been a guiding assumption in cosmology for centuries. But a species evolving in the center of a void would have every reason to believe they were special. They would observe that they occupied the center of an enormous empty region, with the handful of other visible galaxies scattered around them at roughly equal distances. Without knowledge of cosmic voids and the large-scale structure of the universe, they might reasonably conclude that their position was unique and central. This would have profound philosophical implications. Throughout human history, we've repeatedly discovered that we're less special than we thought. Earth is not the center of the solar system. The Sun is not the center of the galaxy. The Milky Way is not the entire universe. Each of these revelations has pushed us further from the center of cosmic significance. But a void civilization might never experience these humbling realizations. They might develop advanced science and technology while maintaining a geocentric, or rather, galaxiocentric, view of their cosmic importance. They would be correct in observing that they occupied the center of a vast empty region, even if they misunderstood what that meant about cosmic structure. Eventually, with sufficiently advanced technology, a void civilization would begin detecting the distant galaxies at the boundaries of their void. They would discover that the universe beyond their local emptiness was filled with structure and complexity. This revelation would be simultaneously exciting and disturbing. Exciting because it would open up an entire cosmos they never knew existed, full of billions of galaxies beyond their immediate cosmic neighborhood. Disturbing because it would force them to reconsider everything they thought they understood about their place in the universe. They would realize that far from being at the center of creation, they actually inhabited one of the universe's least typical environments, a cosmic desert where the usual richness of structure was mysteriously absent. This thought experiment reveals something important about how our observations shape our theories. A void civilization would develop science and mathematics just as we have. Physical laws work the same everywhere in the universe, after all. But their cosmology would be constrained by what they could observe from their particular location, just as ours is. It makes us wonder what we might be missing from our own cosmic perspective. Are there large-scale structures or phenomena that are invisible to us because of where we happen to be located? Are there aspects of the universe's architecture that we can't see because we evolved in a galaxy-rich region rather than somewhere else? While the Boötes Void and the Giant Void lie at enormous distances from us, there exists a large underdense region much closer to home. The local void, located just 150 million light-years away, is one of the nearest substantial voids to our cosmic neighborhood. Though smaller than its more distant cousins, spanning about 150 million light-years in diameter, the local void plays an important role in shaping the structure of our local universe and has been studied in much greater detail than more distant voids precisely because of its proximity. The local void forms part of the boundary of our own cosmic neighborhood, helping to define the edges of the galaxy-rich region where the Milky Way resides. Our local group of galaxies sits near the boundary between denser and less dense regions, with the Virgo cluster and its associated supercluster structures on one side, and the local void on the other. This positioning gives us a somewhat asymmetric view of our cosmic environment. Looking toward Virgo, we see thousands of galaxies clustering together, while looking toward the local void, we see far fewer galaxies spread across a larger volume. Despite being significantly underdense compared to average regions of the universe, the local void is not completely empty. Surveys have identified several dozen galaxies within its boundaries, scattered through the volume like rare lighthouses in a dark ocean. What makes these void galaxies particularly interesting to astronomers is that they provide a controlled experiment for understanding how environment affects galactic evolution. In the dense regions of the cosmic web, galaxies are constantly interacting with their neighbors. They merge together, strip gas from each other, trigger bursts of star formation through collisions, and experience harassment from repeated close passes with other galaxies. All of these interactions strongly influence how galaxies evolve over time. But the galaxies in the local void experience none of these environmental effects. They've spent billions of years in profound isolation, evolving according to internal processes without significant external interference, Studies have found that void galaxies tend to be bluer than galaxies in dense regions, indicating they have younger stellar populations and more active star formation. They also tend to have lower metallicities. Their stars and gas have lower abundances of elements heavier than helium, suggesting they've had less complete stellar evolution compared to galaxies in denser environments. These differences tell us that environment matters profoundly for galactic evolution. A galaxy's fate depends not just on its initial mass and properties, but on where it forms within the cosmic web. The local void OZ plays a dynamic role in our local cosmic environment through its gravitational effects. Though a void contains little matter, it still has gravitational influence through what astronomers call the peculiar velocity field, the pattern of motions that galaxies have beyond the general expansion of space. Matter naturally flows away from underdense regions toward overdense ones, meaning the local void is gently pushing nearby galaxies away from it, while denser structures like the Virgo cluster are pulling galaxies toward them. Our local group experiences both these effects simultaneously. We're being pushed by the local void behind us and pulled by Virgo ahead of us, contributing to our overall motion through space. Understanding the local void's properties in detail has required extensive observational campaigns to identify and measure distances to the faint galaxies within it. This is more challenging than it might seem, because void galaxies tend to be small and intrinsically faint, making them difficult to detect even when they're relatively nearby, in cosmic terms. Additionally, measuring accurate distances to galaxies requires spectroscopy to determine their redshifts, which in turn requires telescope time on major observatories. Mapping the three-dimensional structure of the local void has therefore been a multi-decade project involving numerous surveys and collaborations. The existence and properties of the local void also factor into questions about our cosmic address. Just as the KBC Void hypothesis suggests we might live inside a much larger underdense region, the local void sits uncomfortably close to us, raising questions about whether our immediate cosmic neighborhood is as typical as we'd like to believe. The Milky Way's position near the boundary of a void, rather than deep within a filament or cluster, might not be entirely coincidental. Perhaps there's some selection effect at work. Maybe the conditions suitable for the formation of galaxies like ours, and by extension for the evolution of life and intelligence, are more likely to occur near void boundaries than in other environments. This is speculation, but it highlights how even our nearest void raises questions about cosmic structure and our place within it. The handful of galaxies that manage to exist within cosmic voids represent some of the universe's most isolated objects, and studying them provides unique insights into how galaxies form and evolve in extreme environments. These void galaxies, scattered like rare islands across vast oceans of emptiness, have characteristics that distinguish them from their counterparts in denser regions. Their very existence raises questions about how matter managed to coalesce into galaxies in environments where most material was pulled away toward the void. Boundaries: what were the circumstances that allowed these particular regions to retain enough matter to form galaxies while their surroundings were being emptied out? Research into void galaxies has revealed several consistent patterns. First, void galaxies tend to be late-type spirals rather than ellipticals or lenticulars. This makes sense from a formation standpoint because elliptical galaxies typically form through mergers of smaller galaxies, a process that requires the dense environments of groups and clusters where galaxies frequently encounter each other. In the isolation of a void, such mergers rarely if ever occur, so galaxies retain their spiral structures over cosmic time. Second, These isolated galaxies show evidence of ongoing star formation at rates that are often higher than similarly sized galaxies in denser environments. Their blue colors come from young, hot stars forming in their disks, and their gas reservoirs remain relatively undisturbed by external forces that might strip material away or heat it to temperatures that suppress star formation. The metallicity differences in void galaxies are particularly revealing. In standard models of galactic evolution, galaxies build up their metal content over time through successive generations of stars. Each generation of massive stars fuses hydrogen and helium into heavier elements, then disperses these metals into the interstellar medium through supernova explosions. Subsequent generations of stars form from gas enriched by this process, gradually increasing the overall metallicity of the galaxy. The fact that void galaxies have lower metallicities suggests they've had fewer generations of stellar evolution, either because they formed later than galaxies in denser regions, or because their star formation has proceeded more slowly over time. This gives us a window into understanding how the pace of galactic evolution depends on environment. Some void galaxies exhibit properties that make them appear younger than the universe itself would suggest they should be. They contain large reservoirs of pristine gas, material that has never been processed through stars and retains the primordial composition of hydrogen and helium from the Big Bang. They have lower dust content, which makes sense because dust grains are produced primarily by evolved stars and require multiple stellar generations to accumulate. In many ways, these isolated galaxies resemble what we imagine galaxies looked like in the earlier universe, as if they've been preserved in a state of cosmic adolescence, while galaxies in denser regions have matured into old age. However, not all void galaxies fit neatly into this picture. Some surveys have identified void galaxies that appear quite evolved, with properties similar to galaxies in average density regions. These exceptions tell us that the relationship between environment and evolution is complex and not entirely deterministic. The initial conditions when a galaxy forms, its mass, the density and angular momentum of the gas cloud that formed it, the timing of its formation, also matter significantly. A massive galaxy that formed early in a void might evolve quite differently from a low-mass galaxy that formed late, even though both are in similarly isolated environments. The study of void galaxies also provides tests for our theories of dark matter. Galaxies are thought to form within dark matter halos, invisible structures composed of exotic particles that don't interact with light, but exert gravitational influence on normal matter. In dense regions of the cosmic web, dark matter halos merge together frequently, growing larger through hierarchical assembly. But in voids, halos remain isolated, evolving in relative solitude without frequent mergers. This means void galaxies offer cleaner tests of how dark matter halos grow through accretion of material from their surroundings rather than through mergers with other halos. By comparing the properties of void galaxies with predictions from dark matter simulations, astronomers can test whether our models of dark matter correctly predict how these halos should evolve in underdense environments. One of the most intriguing aspects of void galaxies is their contribution to understanding the cosmic web's formation and evolution. These galaxies mark the locations where, despite the general trend of matter flowing out of voids toward filaments, enough material remained concentrated to allow galaxy formation. Understanding why these particular locations retained matter while their surroundings emptied out can tell us about the detailed physics of how the cosmic web developed. It may relate to the specific pattern of density fluctuations in the early universe, where certain small-scale peaks in density were able to resist being absorbed into larger-scale structures at void boundaries. Recent surveys using sensitive instruments have also revealed that some voids contain even more galaxies than previously thought. But these galaxies are extremely faint dwarf galaxies that were below the detection limits of earlier surveys. This discovery has complicated our understanding of how empty voids truly are. While they certainly contain far fewer galaxies than typical regions, the presence of numerous faint dwarf galaxies suggests that star formation did occur throughout these regions, just primarily in smaller systems rather than large spirals. This raises questions about what determines whether underdense regions form a few large galaxies or many small ones, and how the initial conditions in the early universe influence this outcome. The discovery of the dipole repeller in 2017 introduced a fascinating new perspective on how voids influence cosmic motion. Unlike the voids we've discussed so far, which were characterized primarily by their emptiness and extent, the dipole repeller's significance lies in its dynamic influence on our local cosmic neighborhood. The structure gets its name from its relationship with another major structure called the Shapley concentration. And together, these two regions help explain a long-standing puzzle about the motion of our local group of galaxies through space. Astronomers have known for decades that our local group is moving through space at roughly 600 kilometers per second, relative to the cosmic microwave background radiation. This motion isn't due to the expansion of space, that's a separate effect, but rather is a peculiar velocity caused by gravitational attractions and repulsions from nearby structures. For many years, the assumption was that this motion was caused primarily by gravitational attraction toward overdense regions, particularly the Great Attractor and the Shapley concentration, massive collections of galaxy clusters located in a particular direction in the sky. Our local group appeared to be falling toward these dense structures under their gravitational pull. However, detailed analysis of our velocity and the distribution of matter in our cosmic neighborhood revealed a problem. The pull from the Shapley concentration and other overdense regions wasn't quite sufficient to explain the full magnitude of our motion. Something appeared to be missing from the equation, some additional influence that was contributing to our velocity but wasn't accounted for, in models that only considered gravitational attraction toward massive structures. The solution came from reconsidering the role of voids, not just as passive empty regions, but as active participants in shaping cosmic flows. The dipole repeller is an enormous underdense region located on the opposite side of the sky from the Shapley concentration, approximately 650 million light-years away. While voids don't generate a repulsive force in the conventional sense, their extreme underdensity means they contribute almost no gravitational attraction compared to the average background density of the universe. In effect, they push matter away, not through actual repulsion, but through the absence of the gravitational attraction that denser regions provide. Imagine being on a small boat between two shores. One shore has people pulling on ropes to bring you toward them, while the other shore is completely empty with no one pulling. You'll move toward the shore with people pulling, but you're also effectively being pushed away from the empty shore simply because there's no one there pulling you in that direction. The dipole repeller works in concert with the Shapley concentration to create what researchers call a dipole flow, a pattern of motion in our local universe where matter is simultaneously pulled toward the Shapley region and pushed away from the dipole repeller region. When both effects are included in dynamical models, they accurately reproduce the observed velocity of our local group. This discovery highlighted that understanding cosmic flows requires considering not just where matter is concentrated, but also where it's absent. The voids are not passive empty spaces, but active components of the cosmic web's dynamics, shaping the motions of galaxies through their very emptiness. The recognition of void repulsion as a significant force in cosmic dynamics has led to a more sophisticated understanding of how structure in the universe influences motion. Traditional models focused almost exclusively on overdensities, clusters and superclusters attracting matter toward them. But a complete picture requires incorporating underdensities as well, recognizing that the cosmic web's architecture consists of both positive and negative features that work together to shape the flow of matter through space. It's similar to understanding topography by mapping not just mountains, but valleys as well. The complete landscape includes both high and low regions, and both influence how water flows across the terrain. The Dipole Repeller also demonstrates how much we still have to learn about our local cosmic environment despite a century of modern astronomical observations. This is not a subtle or distant structure. It's a massive void hundreds of millions of light years across, located in our cosmic backyard, yet its role in determining our motion through space was only recognized recently. This discovery came not from a new observational survey finding previously unknown galaxies, but from applying more sophisticated analysis techniques to existing data, reconstructing the three-dimensional density field of our local universe and calculating how all the overdense and underdense regions collectively influence velocity flows. Understanding structures like the Dipole Repeller has practical implications for interpreting cosmological observations. When we measure properties like the Hubble constant or the abundance of galaxy clusters, we're doing so from a specific location in the universe that has a specific velocity through space relative to the cosmic rest frame. If we don't properly account for our peculiar velocity and its causes, including the influence of nearby voids like the Dipole Repeller, we might introduce systematic errors into our measurements. By mapping the complete density field of our local universe and understanding what drives our motion, we can more accurately correct our observations to determine what a hypothetical observer at rest in the cosmic frame would see. The cosmic web represents one of the most striking features of the universe at its largest scales, a vast architecture of structure spanning billions of light years that contains everything we can observe. Understanding how voids fit into this web requires us to zoom out from individual voids and consider the complete picture of how matter is distributed throughout space. The cosmic web consists of four main components, each playing a role in the overall structure: filaments, walls or sheets, nodes, and voids. Filaments are elongated structures where galaxies are strung out in lines across space, like beads on cosmic strings. These filaments are the densest linear structures in the universe, containing the majority of galaxies and serving as the highways along which matter flows through the cosmic web. They can extend for hundreds of millions of light years, connecting major nodes of structure together into an interconnected network. The filaments themselves have substructure. They're not uniform tubes, but rather contain clumps and groups of galaxies distributed along their lengths, with the density varying as you move along the filament. Where filaments intersect, you find nodes, the highest density regions in the cosmic web where massive galaxy clusters form. These nodes are the metropolitan centers of the universe, places where thousands of galaxies congregate in relatively compact volumes. The richest clusters contain as much mass as 1,000,000 billion suns, mostly in the form of dark matter, but with significant contributions from the hot gas between galaxies and the galaxies themselves. Nodes are where the most violent interactions between galaxies occur, where mergers and collisions are common, and where the intergalactic medium reaches temperatures of millions of degrees from the energy of infalling matter. Between filaments, you often find walls or sheets, flattened structures where galaxies are distributed across two-dimensional surfaces rather than one-dimensional lines. These walls are thinner and less dense than filaments, but still contain significantly more galaxies than void regions. They form the boundaries between adjacent voids, like the walls of a foam where bubbles meet. Some of the largest structures ever identified in the universe are walls, including formations like the Great Wall and the Sloan Great Wall, which extend for over 1 billion light-years across the sky. And then there are the voids, the vast empty regions between these denser structures. The voids are not isolated bubbles, but rather interconnected cavities within the cosmic foam, separated from each other by walls and filaments. In a sense, the cosmic web is less like a spider's web, which is a two-dimensional structure, and more like the internal structure of bread, with dense strands of gluten forming an interconnected network surrounding air bubbles of various sizes. Or perhaps even more accurately, it resembles soap foam, where films of soap solution surround bubbles of air, with the soap accumulating at edges where bubbles meet while the interiors remain empty. This architecture is not random, but rather emerges naturally from the physics of gravitational structure formation, operating on the initial density fluctuations present in the early universe. Computer simulations of cosmic structure formation, which start with the small density variations observed in the cosmic microwave background and evolve them forward in time, according to the laws of gravity and fluid dynamics, naturally produce cosmic webs remarkably similar to what we observe in galaxy surveys. This agreement between theory and observation gives us confidence that we understand the basic physics governing structure formation, even as details and subtleties continue to be refined. The scale of the cosmic web is difficult to comprehend. The largest structures in the web, walls and supervoids, can span 1 billion light-years or more, approaching the size of the observable universe itself. At these scales, the cosmic web represents essentially the largest organized structures that exist. Beyond this scale, the universe becomes increasingly uniform, with the variations in density becoming smaller and smaller as you average over larger volumes. This transition from structured to uniform marks what cosmologists call the end of significant structure formation, the scale beyond which gravitational collapse hasn't had time to amplify density differences since the Big Bang. Understanding the cosmic web is crucial for many areas of cosmology. The abundance and properties of galaxy clusters provide constraints on cosmological parameters, like the density of matter and the nature of dark energy. The distribution of galaxies in filaments and walls traces the underlying dark matter distribution, allowing us to map where most of the universe's mass actually resides. And the voids, by representing regions that resisted collapse and remained underdense, provide complementary information about the same cosmological parameters. By studying the complete web, both the dense and empty regions, astronomers can test cosmological models more stringently than by studying either component alone. The cosmic web also has implications for how we think about galaxy formation and evolution. Galaxies don't form in isolation, but rather within a cosmic context, and their location within the web strongly influences their properties and evolution. Galaxies in nodes experience frequent interactions and mergers, leading to the formation of elliptical galaxies and the suppression of star formation. As gas is heated to high temperatures, galaxies in filaments experience intermediate environments, with some interactions but also more isolation than cluster galaxies. Galaxies in walls are more isolated still, while void galaxies evolve in near-complete solitude. This environmental dependence means that to fully understand why galaxies have the properties they do, we need to understand not just the galaxies themselves, but their locations within the cosmic web, One of the most disturbing aspects of cosmic voids becomes apparent when we consider the future evolution of the universe. The expansion of space is not just continuing, but accelerating, driven by dark energy, a mysterious component that permeates all of space and causes the expansion rate to increase over time. This acceleration has profound implications for the long-term future of cosmic structure, particularly for voids, which will grow larger and emptier as the universe ages. Currently, we can observe galaxies billions of light years away, looking deep into space and back in time to see how the universe has evolved. But dark energy is gradually pushing distant structures beyond our cosmic horizon, the boundary beyond which objects are receding from us faster than light can travel to reach us. Objects that cross this horizon disappear from view, their light unable to ever reach us, no matter how long we wait. As cosmic acceleration continues, more and more galaxies will cross this horizon and vanish from our observable universe. For galaxies within gravitationally bound structures like our local group, this isn't an immediate concern. Gravity holds these structures together strongly enough to resist the expansion of space, so the Milky Way and Andromeda will remain bound to each other, even as the space between galaxy clusters expands. But structures that aren't gravitationally bound will be separated by the expansion. The Virgo cluster, currently about 50 million light-years away and part of our local cosmic neighborhood, will gradually recede to greater and greater distances. Eventually, in hundreds of billions of years, it will cross our cosmic horizon and disappear from view. This process will continue as cosmic time progresses. The local group will find itself increasingly isolated, surrounded by growing voids as neighboring galaxy groups and clusters disappear beyond our horizon. One by one, in 1 trillion years, our descendants, if any conscious observers still exist, would live in a universe where only the galaxies of the local group remain visible, surrounded in all directions by darkness. They would be essentially living in a void of their own creation, not because matter has flowed away from their location, but because cosmic acceleration has pushed everything else beyond the reach of observation. This future state of the universe has disturbing implications for future astronomers. With only the local group visible, they would lack the empirical evidence needed to deduce many aspects of cosmology that we take for granted. They wouldn't be able to observe the Hubble expansion because all the galaxies they could see would be gravitationally bound to them rather than receding. They wouldn't be able to see the cosmic microwave background as clearly because it would have redshifted to such long wavelengths after another 1 trillion years of expansion that it would be nearly impossible to detect. They might not even be able to determine that the universe had a beginning in a hot Big Bang, because most of the evidence for that event would have literally disappeared beyond their horizon. In essence, future observers would find themselves in a situation similar to the void, civilization we imagined earlier, living in a universe that appears empty and isolated, with limited evidence about cosmic structure beyond their immediate neighborhood. But unlike our hypothetical void civilization, which lives in an actually underdense region surrounded by galaxy-rich areas they simply can't see very well, future observers would be in a genuinely empty universe where everything else has been pushed beyond the horizon by dark energy. They would have access to more advanced science and technology than we do, but less information about the universe's structure and evolution. It's a sobering reminder that our current epoch may be privileged from an observational standpoint. We live at a time when the evidence for the Big Bang, cosmic expansion, and large-scale structure is all accessible to our instruments. The expansion and emptying of voids is already occurring and will accelerate as dark energy's influence becomes increasingly dominant. While overdense regions like galaxy clusters resist expansion through their strong gravity, underdense regions like voids have no such resistance. The voids will expand faster than the overall expansion of space, growing larger and emptier as matter at their boundaries is drawn away. In a very real sense, the universe is gradually transforming from its current state, where matter congregates in a cosmic web with voids scattered throughout, to a future state where isolation and emptiness dominate, with rare islands of structure surrounded by vast oceans of nothing. This transformation raises deep questions about the ultimate fate of structure in the universe. Will galaxies themselves eventually be torn apart by cosmic expansion? Current evidence suggests not. The acceleration caused by dark energy, while sufficient to push unbound structures apart, isn't strong enough to overcome the gravity holding galaxies together. But this conclusion depends on the properties of dark energy remaining constant. If dark energy's density increases over time, as some theoretical models suggest, the acceleration could eventually become strong enough to disrupt even gravitationally bound structures in a scenario called the Big Rip. In such a future, everything from galaxy clusters to stars to atoms would eventually be torn apart by ever-accelerating expansion. Even if dark energy remains constant and bound structures survive, the long-term future remains bleak from the perspective of complexity and structure. Stars will exhaust their fuel and die, and after trillions of years, star formation will cease as available gas is depleted or dispersed. Galaxies will fade to darkness as their stellar populations age and die without being replaced. Black holes will slowly evaporate through Hawking radiation over incomprehensibly long timescales. Eventually, the universe will consist primarily of empty space with occasional remnants of dead matter scattered through it, a state of maximum entropy where nothing interesting can ever happen again. The voids in this final state will have won. The entire universe will have become essentially a single vast void, with occasional quantum fluctuations, the only events breaking the eternal silence. The methods by which astronomers detect and map cosmic voids represent sophisticated applications of observational technique and computational analysis. You cannot simply point a telescope at the sky and see a void the way you might see a galaxy or star cluster. Voids are defined by the absence of luminous matter, which makes them invisible in direct imaging. Instead, detecting voids requires painstaking surveys of galaxy positions and distances, followed by statistical analysis to identify regions where galaxies are anomalously sparse. The fundamental technique underlying void detection is the redshift survey. When astronomers observe a distant galaxy, its spectrum shows characteristic emission and absorption lines at wavelengths shifted toward the red end of the spectrum due to the expansion of space. By measuring this redshift, astronomers can determine how fast the galaxy is receding from us, which in turn reveals its distance through the Hubble relation. More distant galaxies recede faster, so measuring velocity gives you distance. This technique allows astronomers to create three-dimensional maps of cosmic structure, plotting not just where galaxies appear on the sky, but how far away they are in space. Creating a comprehensive redshift survey requires enormous observational effort. For each galaxy, astronomers must obtain a spectrum, not just a picture, but a detailed measurement of how bright the galaxy is at each wavelength of light. This requires pointing telescopes at individual galaxies or small groups of galaxies and exposing for sufficient time to collect enough photons to create a high-quality spectrum. For bright nearby galaxies, This might take only a few minutes, but for faint distant galaxies, it can require hours of observation. Multiplying this by millions of galaxies means that comprehensive surveys require thousands of hours of telescope time, often distributed among multiple observatories and stretched over many years. The Sloan Digital Sky Survey, one of the most comprehensive redshift surveys ever conducted, exemplifies the scale of effort required to map cosmic structure. This project used a dedicated telescope in New Mexico to systematically image and measure spectra for millions of galaxies across roughly a third of the sky. The survey required over a decade of observations and generated an unprecedented database of galaxy positions and distances. The resulting three-dimensional map revealed the cosmic web in exquisite detail, showing filaments, walls, clusters, and voids spanning the observable universe. Similar surveys, including the 2-degree field galaxy redshift survey, the Vipers survey, and others, have contributed additional data, allowing astronomers to build increasingly complete pictures of large-scale structure. Once astronomers have a three-dimensional map of galaxy positions, identifying voids requires sophisticated algorithms. The simplest approach might be to divide space into cells and count galaxies in each cell, then identify cells with unusually low counts as void regions. But this method is sensitive to the cell size you choose and doesn't naturally identify void boundaries or account for the irregular shapes that voids actually have. More sophisticated techniques use various statistical methods to identify underdense regions while accounting for the complex geometry of real voids. One common approach involves watershed algorithms, originally developed for image processing. These algorithms treat the galaxy density field like a topographic map, with high-density regions as mountains and low-density regions as valleys. Water flows downhill in this landscape, and the boundaries where watersheds meet define natural divisions between regions. Applied to the cosmic density field, these algorithms identify voids as basins in the density landscape, with void boundaries naturally defined by the watersheds separating them from surrounding denser regions. Another approach uses sphere-based algorithms that try to identify the largest possible sphere that can be placed at each point in space while containing no galaxies, or only galaxies below some threshold density. These algorithms build up catalogs of spherical voids of various sizes, which can then be analyzed statistically to understand void properties. Yet another method uses the Voronoi tessellation, a mathematical technique that divides space into cells based on the positions of galaxies, with each cell containing all the points closer to one particular galaxy than to any other. Voids appear as collections of unusually large Voronoi cells, identifying regions where galaxies are far from their nearest neighbors. Each of these methods has advantages and disadvantages, and different algorithms can identify somewhat different sets of voids from the same data. This has led to ongoing debates in the astronomical community about the best way to define voids and measure their properties. Is a void defined by the absence of all galaxies above some mass threshold, or by the overall density being below some value? Should we measure void sizes by their maximum extent, their average radius, or the radius of an equivalent sphere with the same volume? How do we handle voids that overlap or have complex shapes? These questions don't have simple answers, and different research groups often use different definitions depending on their scientific goals. Despite these technical complications, there is general agreement on the basic catalogue of major voids. Structures like the Boötes Void, the local void, and the giant void are identified by all reasonable algorithms, even if the exact boundaries and sizes vary somewhat between analyses. The existence of cosmic voids as a fundamental feature of large-scale structure is unambiguous. even if the precise details of individual voids remain subject to methodological choices. Modern computational techniques have enabled increasingly sophisticated void analyses. With datasets containing millions of galaxies, identifying and characterizing all voids requires significant computational power. Researchers use high-performance computing clusters to analyze survey data, running algorithms that must compare each potential void location with thousands of nearby galaxies to determine local density and identify underdense regions. These computations can take days or weeks, even on powerful computers, but they produce detailed catalogues of void properties that can be compared with theoretical predictions from cosmological simulations. The void catalogues produced by these analyses have enabled statistical studies of void populations. Rather than focusing on individual famous voids, astronomers can now examine how many voids of different sizes exist, how empty they are on average, how their properties correlate with surrounding structures, and how void statistics have changed over cosmic time by comparing surveys at different distances. These statistical studies provide powerful tests of cosmological models because the abundance and properties of voids depend sensitively on cosmological parameters like the matter density, the dark energy equation of state, and the spectrum of initial density fluctuations. Among the largest structures ever identified in the universe, the Sloan Great Wall stands out as a monument to cosmic architecture on the grandest scales. Discovered in data from the Sloan Digital Sky Survey in 2003, this structure consists of an enormous concentration of galaxies forming a wall that extends approximately 1.4 billion light-years in its longest dimension. It contains numerous galaxy clusters and groups, connected by filaments, all part of a single coherent structure that represents one of the most massive assemblages of matter in the observable universe. The Sloan Great Wall is not a solid structure, but rather a complex network of overdensities forming a wall-like geometry in three-dimensional space. Imagine a sheet or membrane stretched across space, with galaxies concentrated along this surface, while the regions on either side of it contain far fewer galaxies. The wall itself has thickness. It's not an infinitesimally thin surface, but rather a flattened structure, perhaps 50 million light-years thick, but over a billion light-years in its longer dimensions. Within this wall, matter is not uniformly distributed, but rather forms substructures like clusters connected by filaments, all oriented roughly along the plane of the wall. What makes the Sloan Great Wall particularly relevant to understanding voids is that this massive overdense structure is bordered by equally massive voids on either side. The wall marks the boundary between two enormous underdense regions, and its formation is intimately connected to the evacuation of matter from these surrounding voids, as gravity pulled matter away from the underdense regions toward the overdense boundaries. The contrast between wall and void became more extreme over cosmic time. The wall grew denser as more matter accumulated there, while the voids grew emptier as matter drained away from them. This relationship between the largest overdensities and the largest voids illustrates a fundamental principle of cosmic structure. Overdense and underdense regions are two sides of the same coin, both products of gravitational instability amplifying initial density fluctuations. You cannot have one without the other. Creating a dense wall requires evacuating matter from surrounding regions, and evacuating matter from voids requires somewhere for that matter to flow. The cosmic web's architecture reflects this complementarity, with each dense structure having associated voids and each void being bounded by dense structures. The discovery of the Sloan Great Wall sparked discussions about whether even larger structures might exist in the universe. Is there a maximum size for coherent structures, or could there be walls and voids extending across even greater distances? cosmological theory suggests there should be a maximum size related to the horizon scale in the early universe, roughly the distance light could travel in the time available for density fluctuations to be established. Structures larger than this scale shouldn't exist, because there wasn't enough time for different parts of such a large region to influence each other and collapse coherently. The Sloan Great Wall approaches, but probably doesn't exceed this theoretical maximum, which is reassuring from the perspective of standard cosmology. If we discovered structures significantly larger than the horizon scale, it would require rethinking our understanding of the early universe and possibly invoking new physics. Some researchers have claimed evidence for structures larger than the horizon scale, including certain void complexes and galaxy distributions. But these claims remain controversial. Most cosmologists believe that once properly analyzed with appropriate statistical methods, these apparent superhorizon structures are actually chance alignments of smaller structures rather than single coherent objects. The Sloan Great Wall also provides a striking visual when represented in three-dimensional visualizations of galaxy surveys. In these visualizations, which plot each galaxy as a point in space based on its position on the sky and its redshift distance, the cosmic web structure becomes apparent. You can see filaments stretching across space, nodes where filaments intersect, and vast empty regions defining the voids. The Sloan Great Wall appears in these visualizations as a dramatic sheet-like concentration of points cutting across the survey volume, immediately apparent to the eye, even without sophisticated statistical analysis. It serves as a reminder that despite the statistical and computational methods required to quantify structure, some features of the cosmic web are so prominent that they would be obvious to any observer with access to three-dimensional galaxy positions. Studying structures like the Sloan Great Wall and their associated voids helps us understand the complete statistical properties of cosmic structure. By measuring how much matter is concentrated in walls versus dispersed in voids, we can test whether our simulations correctly reproduce the range of environments that exist in the real universe. By comparing the sizes of the largest walls and voids with theoretical predictions, we can verify that structure formation has proceeded as expected over cosmic history. And by examining how galaxies in the Sloan Great Wall differ from galaxies in voids or filaments, we continue to probe how environment influences galactic evolution across the full range of cosmic environments. The relationship between cosmic voids and dark energy represents one of the most important connections between large-scale structure and fundamental cosmology. Dark energy, which makes up roughly 70% of the universe's energy content, remains one of physics' deepest mysteries. We know it exists because the expansion of the universe is accelerating rather than decelerating, as gravity would suggest. But we don't know what it actually is, whether it's Einstein's cosmological constant, a dynamic field that changes over time, a modification of general relativity on cosmological scales, or something else entirely. Voids provide a unique laboratory for testing dark energy theories because their expansion is directly influenced by dark energy's properties. The expansion of cosmic voids depends on the balance between gravity and dark energy. Gravity acts to slow the expansion of any region, including voids, by pulling matter inward from the boundaries. Dark energy acts to accelerate expansion, pushing the boundaries outward. In overdense regions like galaxy clusters, gravity is strong enough to completely halt expansion and even cause collapse, which is why clusters remain gravitationally bound despite cosmic expansion. In voids, gravity is weak due to the low matter density, so dark energy's influence is relatively more important. This makes voids sensitive probes of dark energy's properties. Specifically, measuring how fast voids expand compared to the overall expansion of space can constrain the equation of state of dark energy, the relationship between its pressure and density. If dark energy behaves like Einstein's cosmological constant, it has a specific equation of state, where pressure equals negative density in natural units. This produces a particular rate of acceleration and a corresponding prediction for how fast voids should expand. If dark energy instead behaves like a dynamic field with a different equation of state, the acceleration rate would be different, and voids would expand at different speeds. By measuring actual void expansion rates and comparing them to theoretical predictions, astronomers can determine which model of dark energy best matches observations. Measuring void expansion requires comparing void properties at different distances, which correspond to different cosmic times due to light's finite speed. By identifying voids at various redshifts and measuring their sizes and emptiness, astronomers can track how void populations have evolved over cosmic history. Voids should be smaller and less empty in the distant past than they are today, with the specific rate of evolution depending on how dark energy behaves. Comparing observed evolution with predictions from different dark energy models allows us to rule out models that don't match the data and favor models that do. This approach is complementary to other methods for studying dark energy, such as measuring the acceleration of cosmic expansion through supernova observations, or mapping the clustering of galaxies across cosmic time. Each method probes dark energy in a different way and has different systematic uncertainties. By combining information from multiple approaches, including void studies, astronomers can build a more complete and reliable picture of dark energy's properties than any single method could provide alone. Another connection between voids and dark energy involves the integrated Sachs-Wolf effect we discussed earlier. The magnitude of cold spots in the cosmic microwave background caused by photons crossing voids depends on how fast the universe's expansion is accelerating. More acceleration means gravitational potentials change more quickly as space expands, which produces larger temperature shifts. By measuring the actual temperature decrements associated with known voids and comparing them with predictions for different dark energy models, astronomers gain additional constraints on dark energy's nature. Voids also feature in modified gravity theories that attempt to explain cosmic acceleration without invoking dark energy. Some theories propose that general relativity breaks down on cosmological scales, with gravity becoming weaker at very large distances. In these theories, the acceleration we attribute to dark energy is actually caused by gravity behaving differently than Einstein predicted. These modified gravity theories make different predictions about structure formation, including how voids form and evolve, compared to standard dark energy models. By measuring void properties precisely and comparing them with predictions from both dark energy and modified gravity theories, astronomers can test whether general relativity actually does break down at cosmic scales, or whether dark energy is real. Current evidence from void studies, combined with other cosmological observations, favors the standard dark energy picture over most modified gravity alternatives. Voids appear to evolve in ways consistent with general relativity plus a cosmological constant, rather than showing the signatures that modified gravity theories would predict. However, the measurements are not yet precise enough to completely rule out all alternatives, and ongoing surveys with better data will continue to test these ideas. The future of void science depends heavily on next-generation surveys that will map cosmic structure with unprecedented completeness and precision. Projects like the Dark Energy Spectroscopic Instrument, which began observations in 2021, aim to measure redshifts for tens of millions of galaxies, creating three-dimensional maps of structure far more detailed than anything previously available. These surveys will identify thousands of voids across a wide range of sizes and distances, enabling statistical analyses powerful enough to detect subtle effects that current datasets cannot reveal. With such data, astronomers will be able to measure void expansion rates more precisely, track void evolution over cosmic time more completely, and test dark energy models with much greater confidence than is possible with current observations. Statistical approaches to understanding voids extend beyond simply cataloging where voids are and how large they are. Cosmologists have developed sophisticated mathematical frameworks for describing the statistical properties of void populations, allowing quantitative comparisons between observations and theoretical predictions. One of the most important statistical tools is the void probability function, which measures the likelihood of finding a void of a given size at a randomly chosen location in the universe. To understand the void probability function, imagine randomly placing spheres of various radii throughout the universe and checking whether each sphere contains any galaxies above some threshold, brightness or mass. The probability that a sphere of a given radius contains no bright galaxies is the void probability function at that radius. For small radii, this probability is relatively high. There are many small regions of space that happen not to contain bright galaxies simply by chance. As the radius increases, the probability decreases because larger spheres are more likely to encompass at least one galaxy. Eventually, for very large radii approaching the scale of major voids, the probability becomes very small but not zero, reflecting the fact that genuine large-scale voids do exist but are rare. The shape of the void probability function, how it changes as you vary the radius, encodes information about cosmic structure formation. If matter were distributed randomly like gas molecules in a room, the void probability function would follow a simple mathematical form called the Poisson distribution. But galaxies are not randomly distributed. They're clustered together through gravitational attraction, which creates more structure than random distribution would produce. This clustering affects the void probability function, causing it to deviate from the Poisson prediction in ways that depend on the strength and nature of gravitational clustering. By measuring the actual void probability function from galaxy surveys and comparing it to theoretical predictions, cosmologists can test whether their models of structure formation correctly describe how matter clusters over cosmic time. The void probability function is particularly sensitive to certain cosmological parameters that other statistical measures struggle to constrain. For instance, the abundance of large voids depends strongly on the normalization of the matter-power spectrum, a parameter that describes the amplitude of density fluctuations on different scales. If this normalization is higher, meaning density fluctuations were stronger in the early universe, gravitational clustering is more efficient and voids empty out more completely. This produces fewer large voids because matter evacuates more thoroughly from underdense regions and flows into overdense ones, creating a more extreme contrast between full and empty regions. Conversely, lower normalization means less efficient clustering, which produces more numerous but less empty voids. By measuring how many voids of various sizes actually exist, astronomers constrain this normalization parameter from a different angle than methods based on galaxy clustering or cluster abundance. Another statistical approach involves measuring the size distribution of voids, not just the probability of finding a void of a given size, but the actual number of voids in different size ranges. This distribution follows a pattern that cosmologists can predict from theoretical models. Small voids should be common, medium voids less common, and large voids rare, with the specific numbers depending on cosmological parameters and the history of structure formation. Observations confirm this general trend, but the detailed shape of the size distribution provides additional tests of theory. The shape distribution of voids offers yet another statistical probe. Real voids are not perfect spheres, but rather have complex shapes that can be ellipsoidal, triaxial, or irregular. The distribution of void shapes, how many are nearly spherical versus highly elongated, for instance, reflects the underlying geometry of the cosmic web and the dynamics of structure formation. In simulations, voids form within the cosmic web's architecture, squeezed between filaments and walls in ways that produce characteristic shape distributions. Comparing observed void shapes with simulated ones tests whether simulations correctly reproduce the geometric properties of real cosmic structure. Cosmologists also study void clustering, the tendency for voids to be preferentially located near other voids rather than distributed randomly. Just as galaxies cluster together, voids exhibit clustering in their spatial distribution. This void clustering reflects correlations in the underlying density field and provides information about structure formation on the largest scales, measuring how strongly voids cluster as a function of their sizes and separations yields correlation functions that can be compared with theoretical predictions, offering yet another test of cosmological models. The void galaxy correlation function measures how galaxies are distributed around voids, describing the typical density profile from void centers to their boundaries and beyond. This correlation function reveals how sharply defined void boundaries are and how rapidly density increases as you move from void interiors towards surrounding structures. It also identifies what types of galaxies preferentially exist at different distances from void centers, showing how environment varies from the emptiest regions through transitional zones to the densest structures. All these statistical measures, void probability function, size distribution, shape distribution, void clustering, and void galaxy correlations, provide complementary information about cosmic structure. No single measure captures the complete statistical properties of voids, but together they build a comprehensive picture that can be compared in detail with theoretical predictions. Modern cosmological analyses often combine multiple statistics simultaneously, using sophisticated inference techniques to extract the maximum information from survey data and determine which models best match observations across all measured properties. The statistical approach also helps address a fundamental question. Are the voids we observe consistent with being random features of gravitational structure formation? Or do they require special explanation? Could they be evidence of exotic physics or unusual initial conditions in the early universe? The answer from detailed statistical analyses is that observed voids appear entirely consistent with standard structure formation operating on typical initial conditions. The void probability function, size distribution, and other statistics all match what simulations predict when you start with the density fluctuations measured in the cosmic microwave background and evolve them forward according to known physics. This agreement gives us confidence that voids, despite their unsettling emptiness, are natural consequences of how gravity shapes the universe over billions of years, rather than anomalous features requiring exotic explanations. However, statistics can only tell us so much. There's always the possibility that future observations might reveal rare individual voids, with properties so extreme they can't be explained within the standard framework. This is why astronomers continue cataloguing and studying individual major voids, even as they pursue statistical analyses of void populations. Each extreme void pushes the boundaries of what theory must explain, testing whether our models can accommodate the full range of observed structures or whether something is missing from our understanding. While mainstream cosmology confidently explains voids as natural features of gravitational structure formation, alternative theories have been proposed that attribute different or additional significance to these vast empty regions. Some researchers have suggested that voids might be evidence of processes beyond standard cosmology, pointing to features of void structure or statistics that they argue are difficult to explain within conventional models. These alternative ideas remain minority positions in the scientific community, but examining them helps clarify what we actually know about voids and where uncertainties remain. One class of alternative theories proposes that voids might be remnants of bubble nucleation in the early universe. Some speculative models of cosmic inflation, the rapid expansion thought to have occurred in the first fraction of a second, after the Big Bang, involve phase transitions where space can exist in different states or vacua. In these models, bubbles of different vacuum states might nucleate and expand, with collisions between bubbles leaving signatures in the matter distribution. Proponents of these ideas have suggested that cosmic voids might mark the locations of ancient bubble collisions, with matter having been pushed outward from collision sites, leaving empty regions behind. The mainstream cosmological response to these proposals is skepticism based on both theoretical and observational grounds. Theoretically, the conditions required for bubble collisions to produce void-like structures are very specific and don't naturally arise in most inflationary models. The timing and energy scales would need to be fine-tuned to produce features at the scales, where we observe voids rather than much smaller or much larger scales. Observationally, voids have statistical properties and internal structures consistent with standard gravitational formation, rather than showing the distinctive signatures that bubble collisions would produce. Most cosmologists conclude that while bubble collision theories are interesting in their own right, there's no compelling evidence that observed voids require such exotic explanations. Another alternative approach involves modified gravity theories that change how structure forms compared to general relativity. Some of these theories predict that structure formation should proceed differently in underdense versus overdense regions, potentially creating voids with properties distinct from what general relativity predicts. For instance, certain modified gravity theories predict that voids should expand faster than standard cosmology suggests, or that small-scale structures within voids should have different properties than general relativity would produce. Researchers working on these theories have argued that careful measurements of void properties might reveal signatures of modified gravity that would be difficult to detect in other contexts. Testing these predictions requires extremely precise measurements of void properties across multiple scales and distances. Current observations have not revealed clear signatures of modified gravity in voids, but the measurements are not yet precise enough to completely rule out subtle modifications. As survey data improves, the constraints will tighten, either continuing to confirm standard gravity or potentially revealing discrepancies that might point toward new physics. The scientific process here is healthy. Alternative ideas are proposed, specific predictions are made, and observations are used to test those predictions. So far, the observations have consistently favored standard cosmology, but the door remains open for future discoveries. Some alternative theories have focused on the possibility that the universe's matter distribution is more inhomogeneous than standard cosmology assumes, while cosmologists generally believe the universe becomes increasingly uniform at larger scales, a principle called the cosmological principle. Some researchers have questioned whether this principle actually holds, or whether large-scale inhomogeneities might persist to very large scales. In the most extreme versions of these ideas, cosmic voids are not surrounded by relatively uniform distributions of structure, but rather are nested within even larger voids or inhomogeneities extending to scales comparable to the observable universe. These ideas are controversial because they challenge one of cosmology's foundational assumptions and would require rethinking much of our interpretation of cosmological observations. If the cosmological principle doesn't hold, if we live in an unusually overdense or underdense region compared to the universe at large, then observations made from our location might not be representative of the universe as a whole. This would complicate efforts to measure cosmological parameters and could potentially explain certain observational tensions or anomalies in current data. The mainstream view is that while local inhomogeneities certainly exist, we live in a galaxy, in a group, in a supercluster, possibly in a void, the universe does become statistically uniform at scales of hundreds of millions of light years and beyond. Surveys of galaxy distributions at large scales show consistent patterns in all directions, suggesting we're not in a particularly special location. The cosmic microwave background is extremely uniform across the sky after accounting for our motion through space, indicating the universe was very homogeneous in the past, and simulations starting from homogeneous. Initial conditions successfully reproduce observed structure, suggesting no additional large-scale inhomogeneity is needed. Nevertheless, the possibility of living in a special location can't be entirely dismissed. The KBC Void hypothesis we discussed earlier represents a mainstream version of this idea, suggesting we might inhabit an underdense region that, while not challenging the cosmological principle, could affect our measurements of certain cosmological parameters. This remains an active area of research, with astronomers working to map our local cosmic neighborhood more completely and determine whether we genuinely live in an anomalous region or whether our location is typical after all. What unites these alternative theories is that they take seriously the possibility that voids might be telling us something important about physics beyond what we currently understand. While most cosmologists believe standard gravitational structure formation adequately explains voids, maintaining scientific openness to alternatives is important. The history of physics contains numerous examples where anomalies in observations eventually led to major theoretical advances, from the perihelion precession of Mercury leading to general relativity, to galaxy rotation curves leading to dark matter. If future observations reveal void properties that standard theory cannot explain, it could point the way toward new physics. Until then, the conservative approach is to accept that standard cosmology provides an adequate explanation while remaining alert to potential discrepancies that might emerge as data improves. Beyond their scientific significance, cosmic voids provoke deep philosophical and psychological responses that touch on fundamental questions about existence, meaning, and consciousness. The contemplation of vast cosmic emptiness affects something primal in human psychology: our sense of place, our feelings about isolation and connection, our intuitions about the nature of reality itself. Understanding these psychological dimensions adds another layer to appreciating what voids teach us about the universe and our relationship to it. The sheer scale of cosmic voids challenges human cognition in ways that few other phenomena do. Our brains evolved to navigate environments measured in meters and kilometers, to understand quantities ranging from 1 to perhaps a few thousand, and to relate to timescales from seconds to decades. Cosmic voids operate at scales so far beyond these evolved capabilities that genuine comprehension is nearly impossible. 300 million light-years isn't just a large distance. It's a distance so vast that it breaks our intuitive understanding entirely. We can do the mathematics, we can write down the numbers, but we cannot truly conceive what such a distance means in any visceral sense. This cognitive limitation produces a specific psychological response that philosophers and psychologists have studied in various contexts. What some call the sublime, a feeling combining awe, terror, and a kind of overwhelming recognition of something greater than ourselves. The sublime is often associated with natural phenomena like storms, mountains, or the night sky. But cosmic voids may represent the ultimate expression of this feeling. They are so vast, so empty, so alien to human experience that contemplating them produces a sensation of cognitive and emotional overwhelm. We stand at the edge of our ability to comprehend, looking into an abyss that extends far beyond what our minds can grasp. The emptiness of voids carries particular psychological weight beyond their mere size. This recognition can provoke what some have called cosmic loneliness, a feeling of existential isolation arising from awareness of the universe's vast scales and our own infinitesimal place within it. When we learn that our galaxy is one of hundreds of billions, orbiting one star among hundreds of billions of stars, this alone can produce feelings of insignificance. But voids add another dimension to this feeling. Not only are we small, but we're also surrounded by incomprehensible emptiness. The matter that makes us up, and all the galaxies we can observe, occupies a tiny fraction of space. The universe is not just large, it's almost entirely nothing. And we exist as rare exceptions to nothingness, rather than as typical features of reality. Different people respond to this recognition in different ways. Some find it deeply disturbing, experiencing a kind of existential vertigo or anxiety when confronting the scale and emptiness of the cosmos. The psychologist William James described similar feelings in his discussion of what he called the sick soul. Those who cannot help but be aware of the darkness and emptiness underlying existence. For such individuals, learning about cosmic voids might intensify feelings of meaninglessness or cosmic abandonment, reinforcing a sense that existence is precarious and surrounded by nothingness. Others, however, find cosmic voids inspiring rather than disturbing. From this perspective, the existence of structure within vast emptiness makes that structure more remarkable rather than less significant. The fact that gravity and physics conspired to create galaxies, stars, planets, and life, despite the universe's overwhelming tendency toward emptiness, makes existence feel like a triumph over entropy rather than a futile anomaly. The rarity of matter and complexity becomes evidence of something profound rather than something diminishing. This view aligns with what physicists and philosophers have called the fine-tuning problem, the observation that the fundamental constants of nature seem precisely calibrated to allow complex structure to exist at all. From this perspective, voids remind us how remarkable it is that anything exists rather than nothing. The contemplation of voids also connects to perennial philosophical questions about the nature of existence and non-existence. What does it mean for a region of space to be empty? Even in voids, space itself exists, permeated by fields and the quantum vacuum with its ceaseless fluctuations of virtual particles. Empty space is not nothing, in an absolute sense, but rather a structured something with properties determined by the laws of the physics. This observation has led some philosophers and physicists to argue that true nothingness cannot exist, that existence is in some sense necessary rather than contingent, and that even empty space is a form of something rather than nothing. Yet voids also force us to confront limits in our knowledge and understanding. What determines the structure and distribution of matter in the universe? Why does the cosmic web have the architecture it does, with voids and filaments in particular patterns? Standard cosmology traces these patterns back to quantum fluctuations in the first fraction of a second, after the Big Bang. But what determined those initial fluctuations? Were they truly random, determined by quantum mechanics alone? Or is there some deeper structure or principle that shaped them? And what lies beyond our cosmic horizon, in regions we can never observe because their light hasn't had time to reach us? Are there voids even larger than anything we can see, or perhaps regions with entirely different structures governed by different physics? These questions venture beyond what science can currently answer, entering territory where empirical evidence runs out and speculation begins. But voids provide a concrete anchor for such speculation, a reminder that the universe contains structures so extreme they challenge our understanding and invite us to question our assumptions. The philosophical implications extend to questions of cosmic purpose and meaning. If the universe is predominantly empty, if structure and complexity are rare exceptions rather than typical features, what does this suggest about whether the cosmos has any purpose or direction? The psychological impact of voids also depends on how we frame our relationship to cosmic scale. One framing emphasizes our smallness and insignificance. We are tiny creatures on a small planet in an unremarkable galaxy surrounded by emptiness. Therefore, we don't matter in any cosmic sense. An alternative framing emphasizes our connectivity and privilege. We are made of atoms forged in stars. We're part of the cosmic web's matter-rich structures. We're beneficiaries of billions of years of cosmic evolution that brought structure out of chaos. Both framings are equally valid from a factual standpoint, but they produce very different emotional and philosophical responses. Modern psychology recognizes that contemplating cosmic scales can have both positive and negative effects on well-being and perspective. Some research suggests that experiencing awe at vast scales can actually increase feelings of connection and pro-social behavior, as people recognize their commonality with other humans when confronted with something vastly greater than any individual. Other research suggests that excessive contemplation of cosmic insignificance can contribute to feelings of meaninglessness or depression, particularly in individuals already predisposed to such feelings. The relationship between cosmic contemplation and psychological well-being is complex and individual, depending on personality, worldview, and context. What remains clear is that cosmic voids, more than almost any other astronomical phenomenon, force us to confront these deep questions about existence, meaning, scale, and our place in reality. They are not just objects of scientific study, but also prompts for philosophical reflection and psychological introspection. In studying the universe's emptiest places, we inevitably study ourselves, our cognitive limitations, our emotional responses, our capacity for wonder and dread, and our ability to find meaning in a cosmos that may not have been designed with our comfort in mind. As we conclude this journey through the universe's most terrifying places, we must synthesize what cosmic voids teach us about the cosmos and our place within it. These vast empty regions, stretching across hundreds of millions of light years and containing almost no galaxies, represent far more than astronomical curiosities. They are fundamental features of cosmic architecture, keys to understanding how structure forms and evolves, and mirrors reflecting back our own attempts to comprehend existence at its largest scales. The study of voids reveals a profound paradox. By examining the emptiest places in the universe, we learn some of the most important lessons about how everything came to be. Voids formed through the same gravitational processes that created galaxies and clusters. They are the negative space in the cosmic sculpture, the valleys between the mountains, the silence between the notes. You cannot understand the cosmic web without understanding both its dense and empty regions. Both the matter that clusters together and the space that matter has abandoned voids are not the absence of structure, but rather a different kind of structure. Regions shaped by evacuation and expansion rather than by accumulation and collapse. From a purely scientific perspective, voids have proven invaluable for testing cosmological theories and constraining fundamental parameters. Their sizes, shapes, distributions, and evolution over cosmic time all depend sensitively on how gravity works, how dark matter behaves, what dark energy does, and what the initial conditions were in the early universe. Every measurement of void properties provides another piece of the cosmological puzzle, helping astronomers distinguish between competing theories and refine their understanding of cosmic history. The fact that observed voids match theoretical predictions from standard cosmology, starting with simple initial conditions and evolving according to known physics, provides strong evidence that our basic picture of cosmic evolution is correct. Yet voids also remind us of how much we still don't know. Dark energy remains mysterious despite decades of study, and void's expansion and evolution could help reveal its true nature. The possibility that we ourselves live in a void raises questions about whether our cosmological measurements are as universal as we assume. The statistical properties of the largest voids push against theoretical expectations, suggesting either that we're observing rare but allowed fluctuations, or that something subtle in our models needs adjustment. And the sheer existence of structure in a universe that started nearly uniform remains something of a miracle. Gravity amplified tiny quantum fluctuations into the cosmic web we see today. But the specific patterns and scales that emerged depended on a delicate interplay of forces and conditions that we're still working to fully understand. Looking toward the future, our understanding of voids will continue to deepen. As new surveys map cosmic structure with unprecedented detail and precision. Upcoming projects will identify tens of thousands of voids across vast volumes of space and cosmic time, allowing statistical studies far more powerful than what current data permits. These measurements will test dark energy models with greater confidence, probe the nature of gravity at the largest scales, constrain the properties of dark matter, and verify whether structure formation really proceeded as our theories suggest. The coming decades promise to be a golden age for void science, with observations finally becoming precise enough to distinguish between subtle theoretical predictions that current data cannot separate. The discovery of voids also serves as a reminder of how young our cosmic understanding truly is. The Boötes Void was discovered only in 1981, barely 40 years ago. Before that discovery, cosmologists didn't fully appreciate that such enormous empty regions existed, or that they played such an important role in cosmic structure. This was not ancient history. Many astronomers working today began their careers before voids were well studied or understood. It raises the question of what other fundamental features of the universe we might not yet have discovered or fully appreciated. What structures or patterns exist at scales we haven't yet mapped, or in domains we haven't yet explored? What will future astronomers discover that will seem obvious in retrospect, but remains invisible to us today? The ultimate fate of voids in our accelerating universe adds a poignant dimension to their story. As dark energy drives cosmic expansion faster and faster, voids will grow larger and emptier, eventually dominating the universe's structure. Distant galaxies will disappear beyond our horizon, one by one, leaving our local group increasingly isolated in a growing void of our own. In trillions of years, the universe will have become almost entirely empty, with rare islands of structure separated by horizons. they can never cross. The voids will have won, in a sense, transforming the cosmos from its current state of structured complexity to a future state of terminal emptiness. This trajectory, from an initially uniform early universe through an epoch of structure formation, creating the cosmic web we see today, to a final state of isolated structures separated by ever-expanding voids, represents the full arc of cosmic evolution as we currently understand it. We happen to live during the middle epoch, when structure exists but hasn't yet been pulled apart by expansion, when galaxies cluster together but haven't yet faded to darkness, when the cosmic microwave background remains detectable but hasn't yet redshifted to invisibility. This timing is perhaps fortunate from an observational perspective. We exist at a time when the universe reveals its secrets relatively generously, when evidence for the Big Bang, cosmic expansion, dark matter, dark energy, and large-scale structure are all accessible to our instruments. Yet, there's something humbling about recognizing that our entire cosmic civilization, from the first astronomers who mapped the stars to the future scientists who will probe the nature of dark energy, exists during what may be a brief window in cosmic history when the universe's complexity is at its peak and observability is at its maximum. Before this epoch, the universe was too young and hot for complex structure to exist. After this epoch, expansion will have pulled structure apart and dimmed the lights. We inhabit a cosmic moment that will not last, and voids remind us of this temporal contingency. In the end, cosmic voids force us to reckon with existence at its most fundamental level. They show us a universe that is mostly empty, where matter and structure are rare exceptions to nothingness. They reveal scales so vast that our minds cannot truly comprehend them, only approximate through mathematics and metaphor. They demonstrate that our galaxy, our planet, and ourselves exist not in a typical region, but in an unusual one, clustered with other matter against the gravitational pull toward isolation. They suggest that the comfortable sense of living in a universe full of galaxies and cosmic wonders is an illusion of perspective, that the typical cosmic experience would be one of profound emptiness and isolation. Yet paradoxically, contemplating this emptiness need not lead to nihilism or despair. The voids also show us that structure can emerge from near uniformity, that complexity can arise from simplicity, that the laws of physics naturally generate pattern and organization, even in a universe that begins featurelessly and ends in isolation. The fact that we exist at all, that atoms came together to form molecules, molecules formed cells, cells formed organisms, and organisms became conscious enough to contemplate cosmic voids, is remarkable precisely because the alternative is so much more common. Most of the universe is empty and always will be. That anything exists rather than nothing. That consciousness arose to contemplate existence. That intelligence emerged capable of mapping the cosmic web and measuring its voids. These are facts worth celebrating rather than diminishing. The terror of cosmic voids is real. They are genuinely unsettling, challenging our intuitions about existence and our sense of cosmic significance. They show us a universe vast beyond comprehension and empty beyond imagination. But they also showcase the resilience of structure and complexity, the power of physical law to create order from chaos, and the remarkable nature of our own existence as self-aware patterns briefly emerging from and contemplating the void. In studying the universe's emptiest places, we ultimately discover not just the cosmos, but ourselves, our limitations and capabilities, our smallness and significance, our isolation and connection to the grand cosmic story that began 14 billion years ago and continues unfolding around us. The journey through cosmic voids is simultaneously a journey to the limits of human knowledge and understanding. It takes us to the edge of the observable universe, to the boundaries of what we can measure and comprehend, to the frontier where science meets philosophy and empirical observation meets existential questioning. And like all great journeys of exploration, it transforms us. We cannot learn about voids without changing our perspective on existence itself. We cannot contemplate emptiness at these scales without reconsidering what it means to be, to exist, to matter. The voids will remain, expanding gradually as the universe ages. Long after humanity has vanished, they cared nothing for our discovery of them and will care nothing for our extinction. They are not malevolent, but indifferent. Vast regions of space where almost nothing happens across timescales longer than our minds can grasp. Yet in studying them, we've turned that indifference into insight, transforming empty space into knowledge about how the universe works and what our place within it might mean. This transformation, from ignorance to understanding, from terror to comprehension, represents one of humanity's greatest achievements. And the journey continues as we probe ever deeper into the cosmos's emptiest depths. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.